Okay. So I think I'm going to start again. So I hope you remember what I said. So this is the random variable, and this random variable that's with a distribution that might be known or unknown. So we have the values of these variables. So we are drawing samples. So we are going to find the mean of the sample means. So it's going to be the mean of these sample random variables. We are going to also find the degree of variation, the standard deviation of this mean. So it's going to be the standard deviation of the random variable. So we are going to see that this random variable is going to follow a normal distribution with parameters that are the mean of the sample means, that by definition, we are going to see that this mean of the sample means is going to approximate to the population mean. And this standard error, we're going to call this a standard error, is going to show the variability of this distribution, and it's going to be given by sigma divided by the square root of the sample size, right? So, so I was explaining this. Imagine we have this big population or this population. We are drawing samples, and every time we draw a sample, we are taking the mean. So at the end, we can take the means of these different sample means, and we are going to see that as we increase the sample size, the mean of the sample means is going to approximate to the population mean, and we can find the degree of variation by using sigma divided by the square root of the sample size, and that is going to be called the standard error. So if you keep drawing larger and larger samples, such as rolling 1, 2, 5, finally 10 dice, and calculating their means, so the sample means form their own normal distribution. So the more you are drawing samples or you are increasing the sample size, you are going to realize that that distribution is going to be very close to the normal distribution. So that's the reason I can make the assumption that when the sample is big enough, I don't care what kind of distribution they have, they can be approximated to the normal distribution. So at the end of the rectangular and the exponential, if you notice in the book, there are some suggestions that even in those distributions, you can approximate them to the normal distribution. So this chapter of the central limit theorem, we have an example for the binomial distribution. So we can find the normal approximation to the binomial distribution. So this theorem is very helpful because rather than being computing one by one, so I am going to assume this normal distribution. I am going to treat it as a normal distribution. Even if I don't know what kind of distribution lies, what is the underlying distribution, I can use this big assumption if the sample size is large enough. So the normal distribution has the same mean as the original, and a variance that equals the original variance divided by the sample size. So in this case, we have the standard deviation that is also divided by well, the variance by the sample size. So when we are using the standard deviation, we take the square root of the variance, which is the standard deviations, and then we take the square root of the sample size. So that's the reason we have these values. So this is so the standard deviation, remember, is the square root of the variance. So we have to take the square root of the sample size. So that's a minor thing, but it's good to mention. So if you draw random samples of size n, the distribution of the random variable x, which is the sample means. So remember, I drew my samples, I took the mean, and then I am taking the mean of all the means. So that is called the sample means. So this is called the sampling distribution of the mean. So the sampling distribution of the mean approaches to a normal distribution as n, the sample size, increases. Once again, that is a very good principle. because now we can make use a sample and assume this normal distribution, and we can find the area under the curve. So I have two different parameters. I don't know exactly what is the underlying distribution of this, but because the sample size is big enough, I can find the probability of the event by looking at the C-score, right? So the standard error of the mean, so that is going to be the standard error of the mean. So remember, when we have our C-score, so what we did is we subtract the mean, the population mean, from the random variable and divide it by the standard deviation, right? That was that's what we did from the for the C-score. Now we can also apply the C-score for samples, and once again, sample big enough that we can use the assumption of the normal distribution. So we are going to use the random variable and subtract the mean of the sample means. But remember, the mean of the sample means is nothing else but the population mean. I don't have to compute anything. I'm going to use the population mean as an approximation of my sample mean, the mean of the sample means, and then I'm going to divide it by the standard error. So mx is the average of x, of both x and x bar. So, and this standard error is nothing else but sigma divided by the square root of the sample size. So once again, we are going to call this the standard error of the mean. So we are using samples. So we are looking at populations. So we are going to use this sigma and mu. So we are using samples. We are going to assume that the mean of the sample means is going to be given by the value of mu that I already know. So I need to identify the x, and then I need to find the standard error. So that sounds not very easy to understand until we look at an example. So this is the example. Remember now, what this example is going to tell me is that if the sample is big enough, I am going to be able to use the central limit theorem and assume that this case behaves as a normally distributed case. Do I know that? Well, I really don't know. Like I mean, if I have knowledge of this information, so the time behind the wheel, so it says the average time spent by each driver, spent driving each day, varies by age groups. So people between 15 and 19, they spend 25 minutes. People who are 24 and 20 and 24, 52 minutes. People between 25 and 54, 64 minutes. So that makes sense. You are young and you go to the school, you go to the school nearby, you are a person in the working age, you drive more, right? And as you age, so the time behind the wheel decreases. So probably I can use, and I can say that this is a very big data. This data comes from the US Department of Transportation. Very likely they have information from car insurance companies. They have information from drivers' licenses that they are managing. So the question is the following. Even if I don't know what is the underlying distribution here, I'm going to be assuming that this data comes from a normally distributed data. Furthermore, I have 50 drivers. So I was saying that when the sample size is at least 30, I can use this normal distribution assumption. So in this case, my mu, my sigma, and my x. So those are the values that I want to know. So so this is the case, right? Also, a value that I need to know that is different from the previous cases is the value of n. I need to know the size of my sample. So here it says the following. The graph shows the length of time people spend driving each day. You randomly select 50 drivers, Okay, I know that 50 drivers are gonna be part of my sample size. Ages 15 to 29. So people who are between 15 and 29 and 19, sorry, they drive 25 minutes. So the mean time is gonna be 25 minutes. So what is the probability that the mean time they spend driving each day is between 24/7? So I have 24/7. This is gonna be my X1 and 25/5, right? So what happens here? So we have a sigma. This sigma, as you can see, is the sigma from the population. So we know the mean of the population, we know the sigma of the population. So the sigma is gonna be 1.5. So what can I do with this? Who can tell me what should I do with this? Well, first of all, I'm gonna give you some clues. So I am gonna draw this map here. So let me open another one. So I am going to draw my graph with the values. Just imagine that that goes like this, right? So this is the mean, the population mean is 25, right? So my sigma is gonna be, so let me see this. Yeah. So so my sigma is gonna be 1.5, and then I'm gonna find values between 24/7 and 25/5, right? So that's the question. Find the area under the curve that shows these values, right? So, and the question, the formal question is gonna be, what is the probability that a person that I know drives 25 minutes in average is gonna be driving 24/7 and 25/5, right? So what should I do? Can anybody tell me? Step number 1.
Do you have to find the normal distribution for
Yes. Yes,
I'm
that's,
not sure.
yeah, no. Well, I have to find the values, right? So the goal is to find the area under the curve, right? We have the mean equal to 0 and sigma equal to 1. So I want to find the C-score. Well, probably I don't care too much with the C-score because we have to find the C-score here and then find the area under the curve, right? So I'm gonna use the C-score formula, and then I am gonna use the tables to find the area under the curve, right? What else I can do? Remember, step number 1, close everything and go to your table. What is your table is gonna tell you? Let me decrease this. So if you were using this table, can anybody tell me what should you do?
The standardized.
The standardized, if I want to find the C-score, that might be one thing. What else can we do?
Um,
I will use D. What does D say?
the area between two random variables.
So that is the area between two random variables. What does the D say? It
Use B
says
for each random.
use B. So I'm gonna find the area to the left of this and the area to the left of this, and then I am gonna subtract the lowest from the highest, right? So I'm gonna use B. So I'm gonna say the following. So I'm gonna type the values here. So mu. So in this case, I don't know the mean of this sample, but I know that the population mean is gonna be 25. So I'm going to assume that the sample mean for this sampling distribution is going to be 25. So my mu, which is the population mean, is going to be equal to the sampling distribution, and that is going to be equal to 25, right? So let me do this with the use the symbols. Symbol. So I have the mean, the mean of the population. I don't know the mean of my distribution. I don't know the mean of the sample means, but I know the mean of the population. So it's 25. So I'm going to use that. What else do I know? Do I know sigma? Do I know sigma?
Yes.
Yes, I know sigma. Do I need sigma for my computation? The answer is yes. I need to find the value. So in this case, how much is sigma? 1.5.
1.5.
Then I have what? I have n, which is going to be how much? How many? According to my case,
50.
where is my 50, right? Thank you. Thank you. You are good. So 50. What else do I need? I don't need sigma. I don't need this. I need what is called the standard error, right? Which is going to be equal to sigma divided by the square root of the sample size, right? So that's going to be my value of the standard error. So going back to my case, let me see. This is the thing. So what formula should I use? Here, I'm going to find the value for x1, right? Which is this value, right? 24.7. And I'm going to use the second value, right? Which is 25.5, 25.5, right? Am I correct? Yes or no? Are you guys following?
It's 25 or 2.5. X2.
Oh, 25.5. Okay, thank you. That means that, yes, you are following. So
Yeah.
thank you. So then what we're going to do is we're going to find the area to the left of this, right? In the normal case, if you were using the table, you are going to use the C-score, right? And then after the C-score, you are going to use the table. So in Excel, you are almost forgetting about the C-score, and you are going to find the area under the curve by using this Excel code, right? So I'm going to say the probability that X is less than 24.7, right? Can you guys see? So let me make it bigger. So the probability that the value is going to be less than 24.7, which once again is the area to the left of this C-score. And we're going to also look at the probability that X is going to be less than 25.5, right? Are you guys following? So what should I do? I'm going to use this formula B. I'm going to say equal norm that dist. I'm using this. It's asking me for an X value. So in this case, this is going to be the X value. The mean, which is the mean of the population. I don't have the mean for the sample. I have the mean of the population. I'm going to use that mean. And then I am not going to use sigma. I am going to use the standard error, right? And then I'm going to say true. Why? Because I want the cumulative area to the left of 24.7, right? So the second case, I'm going to use the same formula, norm, that list. I'm gonna measure the area to the left of 25. Then the mean is gonna be 25, 25.5, then 25, and then my standard error again, and then true, right? So what should I do? Well, the probability that X lies between 24.7 and 25.5 is going to be equal. Let me make this bigger. So I'm going to subtract the lowest from the largest, okay? The largest minus the lowest. So that should be the area under the curve, okay? So the only thing that we change it, so remember, this is a sample. And instead of using the variance, we're going to use the standard error. So we have to use the standard error. That's the one that we computed here, okay? Is that clear for everybody? Yes, no, maybe?
I'm not sure why. Can you explain why you use the standard error instead of the standard deviation again?
Well, in this case, that's a very good question. Thank you very much. So when we are looking at, for example, you have a population, so you understand the C-score, right? So the C-score, we are looking at the population, and the main question is, what is the probability that if I choose a person randomly outside of my, like for example, if I go to the cafeteria and I find a person who gets a 65% in the test, so how likely is that? So I have data from the population. I am assuming that if I go to the cafeteria and I choose somebody randomly, that is gonna, so that's gonna be the probability. Let's say 20% of the people got 65 and lower, right? So in this case, we have a sample that is different because we are using a sample to measure the probability of an event. Is that a little bit more clear? So in this case, as you can notice, if we are using this C-score, so we don't have a sample size.
It's been 100 years.
So we don't have a sample size, right? So in this case, what happens is that you are taking population information and assuming that if you want to find a case, so that's the probability of occurrence. So in this case, you are measuring the probability given by this sample size, right? Is that something that?
Yeah, it makes more sense now.
Yeah, so in this case, remember, we are measuring the standard error because we are accounting for the sample size. So in the previous case, we didn't. So I think there is a case at the end of this case. If not, I'm gonna find it. You have the same question. You have that the average debt for people who are taking classes, like the student loans, are $5,000 in average.
It's going to be a player in your life.
You look
Buy
at
this
the.
car, you'll get girl.
Hold on. I'm gonna mute all. So what happened here is that you can find the probability with this information. So if you apply the C-score for the big population, your question might be, how likely is that you find somebody randomly and that student has that debt? So when you are using a sample, the question might be different. So that pertains to the sample. So the question is, sometimes you are using a sample because you don't know the population, or I mean, you have the data from the population and you want to corroborate that those values are true. So you are using a sample. You cannot do population studies because it takes so many resources. So in many cases, this idea of using a sample is going to help us to understand the next steps, because now you want to prove, like for example, the president of Lehman says that 60% of the, well, how to say, he might say women are smarter than men. And you might say, I don't believe it. You are a guy who says, I don't believe it. So you choose a sample and you either confirm or deny what the president is saying about Lehman students, that women are more intelligent than men. So that probably he made that comment based on an article that probably he read in a big journal that says that at the population level, women are smarter than men, or they get better grades than men. So you are skeptical, so you choose a sample. So that's when you use this formula, because you are accounting for the sample that you are taking, right? Is that clear, or am I making too much out of it?
Yeah, it's clear.
Okay, okay. So
Thank
sure, of course. So so in this case, did I get the right results? So in this case, yes, 91.2, 91.16. So basically, that's what we did. We are using the C-score to compute these values in a in a sample. So that is very helpful, because, I mean, as I said before, the president of Lehman is claiming that women are smarter than men. You might say, well, I want to confirm it. Like, for example, another case for that, a car manufacturer, let's say, the guy says, or the CEO says that the car is the highest performer. So it says you can get 100 miles per gallon. And you said, that's too much. So how do you prove or disprove that claim? So you are going to take a sample of 50 cars or 100 cars or whatever the number you can gather, and look at how much gasoline they spend per gallon. So at the end, you will be able to say, well, he was right, or probably no, he wasn't right. So we can look at these values. So our next chapter, so we still have work to do here. Our next chapter is what is called the confidence intervals. So those confidence intervals are going to be very helpful. And then we're going to do hypothesis testing, which is basically finding results for samples and being able to extrapolate that information for the whole population. We are making inference that this sample, how this sample approximates to that particular population. It's beautiful when we are able to look at these values and say, wow, my sample was strong enough that we can predict behavior for the population. But anyways, is there any question additional? Yes, no? So what we are gonna do, I think I'm gonna stop here, because this is the second part, the binomial. Probably, so this binomial is not gonna take me more than one class. So, and that is gonna be good, because you will have enough time to complete your assignments. So the next chapters, as I mentioned, confidence intervals and hypothesis testing, they are really big. So it's like going back to the first class where we have so much information. I will try to make it very simple. And so, so next class, we're gonna continue with the class. We're gonna look at the normal approximation to the binomial. That is very interesting. You remember the binomial, the probability of success and the probability of failure. And you remember, if you multiply n times p, you can get the mean. And if you multiply n times p times q, you find the variance, you take the square root, you find the standard deviation. So we can build and also assume that we can use the normal distribution in order to find the area under the curve. So we are going to make some provisions, and some of them have to do with this table. So please keep an eye on this, because that's going to be like the little information that we might need for understanding this problem. Okay, so I will see you guys next class unless you have a question. And so I have 2 people in the